Welcome to all of you. In this video, I am going to discuss about octane number and its significance. Octane number is one of the most important quality parameter of petrol or gasoline or motor spirit. So in this video, I am going to discuss about all different aspects of octane number. So I will discuss about why octane number is important, what will happen when octane number will be low, and what will be benefit when octane number will be high. Octane number will be high. I will also discuss about how octane number is determined, and I will also discuss about what type of hydrocarbon molecules or what type of molecules in general having a high octane number and what type of molecules having low octane number. And finally, I will discuss a practical aspect of octane number, that whether we should go for high octane number for our car. I mean, whether we should purchase a petrol which is having high octane number or a moderate octane number will suffice. So all these things will be discussed in detail in this video, but before I directly jump over the practical definition or the standard definition of octane number, let us first discuss about spark ignition engines working principle, because petrol is usually used in a spark ignition engine, and to understand importance of octane number, or to comprehend or to justify the importance of octane number, we need to first understand how a spark ignition engine works. So a spark ignition engine basically is a 4-stroke engine which consists of intake, compression, power and exhaust strokes. So basically it consists a cylinder and a piston, and with the help of crankshaft it moves up and down. This piston moves up and down. Basically, in intake stroke, the cylinder moves downward. The piston moves downward, and because of this movement of piston, it creates a low pressure region in this cylinder. And because of that region, at that time, intake valve opens, and the fuel air mixtures enters into this cylinder. Now, in the compression stroke, this piston moves in upward direction, and because of that this fuel air mixtures pressurized, and its pressure and temperature increases. At this stroke, inlet valve, intake valve as well as exhaust valve remains in closed position. Now in third stroke, what happens when this piston moves at the uppermost possible position, then what happens, this spark plug ignites the spark, and because of that the combustion reaction start taking place. And due to combustion reaction, the volume expanded or the pressure increases because of this combustion reaction, so it will move the piston in downward direction, and this is also called power stroke, and this is the reason for which we are doing all these things. So this provides the energy to the car or any motorcycle or bike. So in the last step, finally when combustion reaction completed, then exhaust gases form like CO, CO2, H2O, nitrogen, or onboard hydrocarbon, NOx, SOx, whatever the thing will be. In last stage, again piston moves upward, and this exhaust valve open, and this whatever the streams, exhaust stream goes outside into the atmosphere. So this is the basic 4 steps of a spark ignition engine. Basically it works on thermodynamic cycle called Otto cycles. So in ideal situation, it works smoothly. Or to work smoothly, what should happen, that when this piston moves at this uppermost position, then as this spark plug should ignite this fuel air mixtures, and when due to this ignition by the spark plug, there should combustion reaction should start. This should be the ideal condition for a smooth running of this engine. But what happens when this piston moves in compression stage? So what may be possible is that due to this compression, this fuel air mixture pressure increases. Now it may be possible that due to high pressure, because due to compression pressure increases, and we know that for gases or vapor, as pressure increases its temperature also increases. So due to high pressure at high temperature, this fuel air mixtures may ignite spontaneously without any need of a spark by a spark plug. This is called auto ignition. So what happened when during this upper movement of this piston, it may be possible that this fuel air mixture may ignite prematurely. This is also called pre-ignition. And because of that reason, due to this pre-ignition, this air fuel mixture combustion reaction starts, and because of that reason this pressure wave front will form, or the spark front or the flame front will form, and this will try to move this piston in this lower direction. But due to this crankshaft movement, piston will try to push in upper direction, and because of these two different direction motion, when these two front moves, I mean the pressure front of combustion reaction and this piston hit each other, then knocking sound creates like a metallic sound kind of things. So because of this reason, this may be very detrimental to engine, and this is called knocking. So this is the one mechanism of knocking. Another mechanism could be possible is that this pre-ignition is not taking place. So it means when piston moves at the uppermost position, this is also called TDC, top dead center. When it moves at this uppermost position, then only ignition started by the help of spark plug. This is okay until this. But what happened when this ignition started, the pressure and temperature increases of this fuel air mixture, and because of that reason, in some part, another part, let's say this compression, because of this spark, flame front is moving in this direction. So ideally what should happen, this flame front, wherever it goes, it should ignite the fuel air mixture, so it should be a smooth burning. But what happened, due to this combustion reaction, it may be possible that some other part of fuel air mixture may ignite without reaching this flame front at that position, and because of that reason another pressure wave front will create, and when this pressure wave both pressure wave front hit each other, again knocking sound arises. So there could be two possible mechanisms by which this knocking may take place, and so I would say that knocking usually occurs when combustion of some of the air fuel mixture in the cylinder does not result from propagation of the flame front ignited by a spark plug. Rather, it ignite outside of normal combustion front, and because of that reason, when these two high frequency pressure waves hit each other, then this creates a very high metallic sound that is called knocking. And when sound is less, then it is called knocking, and sound is very high, then it may be called as detonation. So this is very detrimental to engine because engine is trying to moving in this direction, and this pressure wave front is trying to move in this direction, and because of that reason engine may damage in extreme conditions. So this is unavoidable. Knocking should not take place. So let us understand when knocking will take place. I mean, what goes wrong when knocking will take place. So knocking usually take place when compression ratio of engine is very high. What is compression ratio? Compression ratio is basically defined as the total volume or the maximum possible volume of this cylinder divided by the lowest possible volume of this cylinder. So the maximum possible volume will be when this piston at the lowest possible point, that is called BDC, that is bottom dead center, and so let's suppose the lowest possible point is this, and the uppermost position is say this point. Lowest position is this point. So this is the maximum possible volume for air and fuel mixture, and let's suppose this uppermost point, that is called TDC, is this. So this is called clearance volume. So compression ratio is basically defined as the total volume divided by clearance volume. So let's suppose it is 8, total volume is 8 times of the clearance volume, so then compression ratio will be 8. So when compression ratio goes high, then what happens? Due to high compression ratio, pressure increases very high, and because of that pressure, high temperature reaches, and the fuel air mixture may auto ignited without any help of a spark plug, and knocking may take place. So this is the one possible reason, and the another possible reason is for a given compression ratio, it also depend on the fuel quality. So some type of fuel having high knocking resistance, and some type of fuel having low knocking resistance. So the fuel which does not auto ignite for a higher compression ratio is designated with high octane number. So octane number is basically linked with this anti-knocking property. So I will discuss about this. So basically what happens when compression ratio goes high, the engine efficiency goes high, because for Otto cycle, if you go through any thermodynamics books, then you will find that for Otto cycle engine efficiency basically depend on the compression ratio. So for high compression ratio, engine efficiency goes high, but it will create a problem of knocking, and so for that type of engine, high octane number fuel may be required. So anyway, let us move forward. So this is the same stroke engine and with different nomenclature. So let us jump over to our formal definition of octane number. So basically octane number is a measure of resistance of gasoline to detonation or engine knocking in a spark ignition internal combustion engines. So higher octane rating means higher knocking resistance tendency. And the higher octane number means the more compression of the fuel can withstand without detonation or igniting. So what happens for high compression means more efficiency. So for that type of engine, higher octane number fuel may be required. So that's what it is written. Higher performance engine typically have higher compression ratio and therefore more prone to detonation, so they require higher octane rating fuel. So that's what I was talking about. The compressor or the engine efficiency is basically depend on the compression ratio. This is R is compression ratio, and you will see that when compression ratio goes high, efficiency goes high. So according to fuel consumption understanding, we need to having high compression ratio, but high compression ratio may damage the engine due to this detonation. So the remedy is we may use a high octane number fuel. So for a given high compression ratio, if I increase octane number, then I will solve the knocking problem as well as my efficiency will go high. Okay. So let us understand how octane number is assigned for a given fuel. So basically different type of fuels had been tested for anti-knocking resistance, and what they found that isooctane is having very good knocking resistance. So they just given a octane number for isooctane is 100, and there is another hydrocarbon called N-heptane which knocks very badly, and they assigned octane number 0 for. Okay. So N-heptane, which knocks very badly, is assigned as octane number 0. Now octane number of any fuel is defined as the volume percentage of isooctane in a blend with N-heptane which is having same knocking characteristic as test fuel or given fuel. So for example, any fuel having 90 octane, it means that the fuel having same knocking characteristic as a mixture having 90% isooctane and 10% N-heptane. Okay. So basically how octane number of any fuel is determined. Actually octane number of a fuel is measured in a test engine having a standard and control conditions. I mean single cylinder variable compression ratio engine, that is known as CFR engine, and what it does, it produces a knocking characteristic of a fuel. So for example, in this meter it shows that how much knocking it creating this fuel in this test engine. Now that knocking is compared with a chart which is having for different percentage of isooctane and n-heptane different knocking. So let's say the knocking produced by this test fuel is say 10, and the octane or whatever it may be, I don't know exactly how much value it shows. So let's suppose, just for understanding, it is showing that 10, and the knocking of in the given chart shows that isooctane volume of percent of say 80% and 20% n-heptane produces the same knocking like say 10, then the octane number of that test fuel will be 80. So this way we determine this is called CFR engine, and this is a standard a standard for octane number determination. This is having variable compression ratio and single cylinder. Okay. Now octane number can be determined in different possible way, and based on that octane number is having different types. For example, octane number may be called as research octane number, and this is the most commonly used octane number. It is determined by burning the fuel in test engine which is having 600 rpm and variable compressor ratio, and then the result compared with the mixture of isooctane and heptane. Now in motor octane number, the test of fuel is done in the similar test engine but with different condition. For example, in this case the fuel is generally preheated, RPM of the engine is say 900 RPM, and ignition timing is also variable timing. So basically we are stressing the fuel further, and that octane number the resulted octane number is called motor octane number. So since we are assessing the fuel higher, it means the chances of knocking tendency will be higher, and because of that reason it will show high knocking for the same fuel in this for motor octane number. And so when we compare with that high octane number in the chart, then we will find that it corresponds to lower percentage of isooctane. So basically motor octane number will be lower compared to research octane number. So actually motor octane number is a better measure of how a fuel will actually behave under a higher load than normal load, because research octane number is usually for a lower load, I mean a small car and all those things, and for high speed car motor octane number may be a better indication of octane number. So generally in modern gasoline, generally motor octane number usually remains 8 to 10 points lower compared to the research octane number. However, there is no direct link between research octane number and motor octane number. Now there is another octane number called posted octane number. This is basically the average of research octane number and motor octane number, and this is also called anti-knocking index, AKI. Okay. So this is all about octane number and different types of octane number. So we now understand that a high compression ratio engine may require high octane number fuel. So let us try to figure out what type of molecule having high octane number and what type of molecules having low octane number. So octane number basically depends on type of molecules as well as number of carbons of any hydrocarbons. For example, generally octane number of aromatics is higher compared to paraffins, but this statement will be only valid for a fixed carbon number. Once you reduce the carbon number, octane number usually increases. For example, when you see that the methane having octane number 120 while it is paraffins, while n-heptane which is having 0 octane number, that is very low, and that is a standard. Similarly, when the isomerization take place, then octane number increases. So for example, this is again paraffin, but it is having 100 octane number. Okay. So you may see that this, as molecular weight increases or the number of carbon increases, octane number decreases. Similarly, as branching increases, octane number increases. Olefins having higher octane number compared to this paraffins, and aromatic having even higher octane numbers. Cycloparaffins, that is called naphthenes, is having higher octane number compared to paraffins. Apart from this, there are others oxygenate molecules which is having very high octane number, like ethanols having very high octane number. Different sources shows different octane number. For example, ethanol having 125 octane number, and while in Wikipedia it is given that 108.7. Similarly, methanol having 130 in one book, another Wikipedia 108.7. Methyl tertiary butyl ether, again a oxygenate, having very high octane number. Tetraethyl ethyl lead is also very high octane number. So basically, what we understand from this table, that when carbon number increases, octane number decreases. Oxygenates having very high octane number, aromatics having high octane number compared to paraffins. When branching increases, then again octane number increases. So for a fixed carbon number, let's say, so basically the purpose of this table is, I wanted to convey that we cannot compare two different group of molecules with respect to octane number for different carbon numbers. For example, if you say that aromatics having high octane number compared to paraffins, and based on that, if you think that methane is having higher octane number than benzene, then you are wrong, because that statement will be only valid for a fixed carbon number. So let us discuss for a fixed carbon number. For a fixed carbon number, let us see how octane number varies. So this is paraffin having very low octane number, 24.8. One branching increases octane number up to 73.4. Now this branching, when moves to center, then octane number increases further, 74.5. Even more branching, octane number moved to 91.8, and this branching position again affect the octane number. So 2,3-dimethylbutane having octane number very high, 104. Again, naphthenes having octane number higher compared to the paraffins, but again, if high branching, then it may be lower than even isoparaffins. So you cannot compare with isoparaffin with naphthenes, because for example, if you compare with 2-methylpentane with cyclohexane for a fixed carbon number, then you will find that naphthenes having higher octane number compared to the isoparaffin. But if you take example of say 2,2-dimethylbutane, that is having even higher branching, higher number of branching, then it will be having higher octane number compared to the naphthenes. Again, even in naphthenes, when branching take place, then octane number increases. For example, methyl cyclopentane having octane number as 91.4. Olefins, again olefins having higher octane number compared to the paraffins, but again, even in olefins, the branching increases octane number. For example, 2-methyl-1-pentene having octane number 96.1. And in cycloolefins, octane number is higher compared to just a normal estate olefins. And finally, for aromatic, octane number will be very high. So based on this understanding, what we understand that there is no direct ascending or descending order of octane number for different types of or different family of molecules. We cannot say that aromatics having higher octane number than olefins compared to the naphthenes, and naphthenes having higher octane number than isoparaffins, and isoparaffins having higher octane number than paraffins. This statement will be wrong, because even one type of isoparaffins having higher octane number than benzene, for example, for even for fixed carbon number. Similarly, for naphthenes, you may say that some it may be having higher octane numbers, for example cyclohexane, compared to this one type of isoparaffins, but another type of isoparaffins having higher octane number compared to this naphthenes, and same goes true for olefins. So there is no direct relations, it depends on the structure of molecules. But what we can Similarly, the same discussion is shown here. This is for again for same 6 carbon molecules. I have just shown the structure of the different molecules. And again for 6 carbon molecules, again I have shown the structure of different type of molecules. So again this is a graph which shows that as carbon number increases, octane number of different family decreases, but for a fixed carbon number there may be different relations at different different carbon number. For example, for carbon number 6 there may be this relation, but for carbon number 9 there may be this relationship. So you cannot say. So what I can say with certainty is that octane number is usually lowest for straight chain hydrocarbons and highest for aromatic hydrocarbon with olefins and naphthalene in intermediate position. But for a paraffinic hydrocarbon, octane number increases by shortening the main chain. I mean, when carbon number increases in a paraffin hydrocarbon, then octane number increases. For example, methane having very high octane number. Again, when branching take place, for example, side chain as methyl groups in a paraffin hydrocarbon, then octane number increases. More branching means more octane number. And again, even branch will be in at central position, then octane number will be higher. For example, if you see this, 2-methyl pentane having 73.4 octane number, while 3-methyl pentane having 74.5 octane number. Okay, for olefin hydrocarbon, all these 3 points will be valid, and again for olefin hydrocarbon, when the double bond goes towards the center, then octane number increases. For example, so let's suppose this is a olefin, it is having 96.1 octane number, and if suppose double bond goes at this position, then octane number will be higher. Now for naphthalene hydrocarbon, octane number increases by decreasing the size of the ring, again the same thing, or for decreasing the length of largest unbranched side chain. I mean, when there will be branching, then again branching in the side chain, octane number increases. At the same time, distributing the carbon atom in the side chain into many short chains rather than one long chain. So it is concerned with branching. And finally, centralization of the side chain. So in the side chain, if the branching is at the center position, then octane number increases. Now let us discuss about our last point, that whether we should go for high octane number fuel for our car, or whether it is beneficial or not. For example, because in market sometimes you will find that on some petrol pump, some petrol having octane number say 91, another having octane number 95, another having octane number 97. So whether it is beneficial to go for high octane number fuel or not. So basically high octane number fuel cost high, so we should understand that which type of petrol we should fill in our fuel tank. So basically if my car is designed such that, I mean, the car having compression ratio such that say it is there won't be any knocking for octane number say 91 or higher, then in that car if you are using 95 octane number, then it is wastage of money, because the car is designed for a given compression ratio. So octane number, a high octane number will be beneficial only when your car compression ratio also increases. So you cannot increase compression ratio. So it means for a given car, if that car is defined for say 91 octane number, then you should use only 91 octane number. But if some very high speed cars, like very costly cars, they may be designed for a high compression ratio. In that car, if you are using for let's say 91 octane number, then that car may knock, and then that may damage your car. So basically you should check your car manual that what should be octane number of your fuel in your car. For example, I have a Hyundai Accent, and in that manual it is written that your new vehicle is designed to use only unleaded fuel having an octane rating of RN 91 or anti-knocking index 87 or higher. So for me 91 octane number will suffice. But suppose you have any bike or any car which shows the in that manual it is written that octane number required say 95. So in that case you may need higher octane number fuel. So higher octane number will not improve performance because compression of the engine won't change. So basically which type of octane number petrol you should fill in your car basically depend on the type of your car. Okay, so I hope all the different aspects of octane number I have discussed, it will be helpful, and in the next video I will discuss about the different quality parameters in BS4 for petrol. What are the different quality parameters and why that quality parameter has been imposed in BS4. I will discuss in detail in next video. Thank you for watching.